So I want to highlight the differences between a radian and a steradian. Now that we're into radiation in more detail, we come across this unit of a steradian, and it's a little bit kind of conceptually, for me anyway, kind of conceptually difficult at first. But you're familiar with the idea of a radian. We know, for example, that there are 2 pi radians. If we take 2 pi radians and multiply by the radius of a circle, we'll come up with the circumference of that circle. So this circle, for example, the radius of it is given by the letter r, and we multiply it by 2 pi. We go all the way around the circle, and we come up with its circumference. If we wanted to figure out the length of an arc, we take, if there was some angle at the center of the circle, and multiply this angle in radians, so we've got theta radians, multiply that by the radius of the circle, and you'll come up with the length of the arc subtended by the angle theta at the center of the circle. So this word subtended means we've got an arc, and this arc is defined by some angle theta. So in this case, it's defined by this point right in the center with angle theta. So the length of this arc, the length of the arc subtended by the angle theta at the center, is this length right here in red. Another way to express this would be the fraction of the total circumference of the circle. If we take that fraction and multiply it by 2 pi, you'll come up with the number of radians for this angle. For example, this angle right here might only be 40% of the way around. If you take that 40%, or actually 20% or so, take that 20%, multiply by 2 pi, and you'll get the angle theta in radians. So let's say, for example, we are 1/4 of the way around the circle. So the theta in this case, the angle would be pointing straight up and down. There'd be we could draw another blue line, for example, 1/4 of the way around. Multiply that by 2 pi. So here we've got 1/4 times 2 pi. And that equals pi over 2 radians, or what we know as 90 degrees. So a 90-degree angle makes a length of the arc that's 1/4 of the way around the entire circle. The analogy between a radian and a steradian, we're going to go from a 2-dimensional concept to a 3-dimensional concept. So instead of being 1/4, or instead of looking at the fraction of the total circumference of a circle and multiplying that by 2 pi, we're going to look at the fraction of the total area of a sphere and multiply it by 4 pi. And just as we got radians, the number of radians in the 2-dimensional case, we'll come up with the number of steradians in the 3-dimensional case. The first thing that came to mind to me when I started studying this material is the Death Star in Star Wars. And you have this little array up here, the laser thing that it shoots. And we could figure out the fraction of the total area of the Death Star comprised by this little area right here. And that would give you what's called a solid angle in steradians. And we could make that calculation. So let's take a look at it in geometrical form. We look at it this way: the fraction of the area on a circle, if we have some other area on the surface of it, the fraction of this area multiplied by 4 pi will give us the number of steradians. And this doesn't have to be a circle. I drew a circle because it matched the Death Star, but it could be any kind of mass like this. And we say that this circle is subtended by a solid angle at the center of this larger sphere. So this arbitrary surface area here is subtended by the solid angle at the center of it. And both of these will have units of steradians. And in both cases, we figure out the area of them and divide by the total area of the sphere, multiply that by 4 pi, and we can come up with the number of steradians. I want to demonstrate this by using a couple of common examples. And one of which is, if we think about the moon, think about looking up at the moon from the Earth. The diameter of the moon is about 2,200 miles. So if you dug a hole through it, you dug for 2,200 miles, you'd come out on the other side of the moon. The projected area that we're seeing then is the area of the circle when we look up at the sky, looking at the moon. We have pi over 4 times the diameter of the moon squared, and we come up with something close to 4 million square miles. The distance of the moon from the Earth is about 240,000 miles. So the area of this celestial sphere, we've got the Earth here, the Moon 240,000 miles away from us. The area of this celestial sphere is 4 pi times the distance of the Moon from the Earth. So 4 pi r squared, effectively. So we make that, do the math, we come up with an area of this celestial sphere of 7.2 times 10 to the 11th square miles. So we want to figure out the ratio, the fraction of the Moon's area to the area of this whole sphere. So we take the area of the Moon, about 4 million square miles, and multiply it by about 7 times 10 to the 11th square miles. Multiply that by 100%, we could find out that the Moon occupies about 0.0005% of the celestial sphere. So it occupies a very small surface area of this whole sphere that we would see in the sky. The whole sphere itself comprises, if you looked up in the night sky, all the sky that you could see, and then you look down at the ground and down by your feet, everywhere around it, the whole sphere would occupy 4 pi steradians. The Moon itself occupies 4 pi times 5.3 times 10 to the minus 6, the fraction of the whole sky, and the Moon occupies about 7 times 10 to the minus 5th steradians. So here's the area of the sky that the Moon occupies. Let's contrast this with the Sun. So you think about the Moon in the sky, think about how the surface area of that, and let's think about the Sun, the fraction of the Sun that occupies the night sky. So again, we do something similar. The diameter of the Sun is 865,000 miles. The projected area, therefore, is pi over 4 times r squared, or times the diameter squared. It's 5.9 times 10 to the 11th square miles. The Earth is 93 million miles away from us, so the area of its celestial sphere is 4 pi times 93 million miles squared, or it's about 1.1 times 10 to the 17th square miles. So let's do the same thing we did with the Moon. We're going to take the fraction of the area of the celestial sphere occupied by the Sun, multiply that by 4 pi, we'll come up with the number of steradians that the Sun occupies in the sky. So we take this 5.9 times 10 to the 11th, the area, the projected area of the Sun, divide that by the area of the celestial sphere, multiply by 4 pi, and we come up with a value of 6.7 times 10 to the minus 5th steradians. Compare this number, about 7 times 10 to the minus 5th, with that of the Moon. We get to two significant figures, we get the exact same value. So you can imagine the Moon, during an eclipse, the Moon completely eclipsed the Sun. It's right at the same size, and you see that corona that coming off from the edge of the Sun. So it's really interesting. The Moon and the Sun occupy the same area in the sky. We can calculate that using steradians. So now I was curious, what part of my hand, now that we know this, with the Sun and the Moon, they occupy the same area of the sky, what part of my hand, if I held it at arm's length, is needed to completely cover the Moon or the Sun? And I took a measurement. My hand is about 28 inches from my eye, just using a tape measure. The area of the sphere, then, if I swept out a sphere with my hand held at a distance from my eye, I come up with an area of about 10,000 square inches. The number of steradians, then, is 4 pi times this small area divided by the area of the entire sphere. And this small area is what I want to calculate. And the small area in this case would be the area of the Moon or the area of the Sun as we're holding our hand out. So the small area then is the number of steradians that we calculated for both the Moon and the Sun. They happen to be the same. Multiplied by the area of the sphere, if I swept it out with my hand, divided by 4 pi. So the area of my hand needed to cover the Sun is a 6.7 times 10 to the minus 5th times the area of the sphere swept out by my hand divided by 4 pi. And I come up with a value, an area of about 0.05 square inches. And that's equivalent to a square that, if we take the square root of this thing, a square that is smaller than a 1/4 inch on a side, or smaller than 6 millimeters on a side. And I did a measurement, and this is smaller than my little fingernail. So according to these estimates, I haven't done the experiment yet, but if you went outside on a night with a full moon and you held your fingernail, your little fingernail in front of the moon, you're liable to cover the entire thing. And that's really surprising to me. I think about the moon being a very large object, but I think it seems large on a relative scale. We see it For example, when it's rising, we see it coming up behind trees, which we associate with a real large thing, and we make that connection with the moon. But give that a shot. Cover the moon with your little fingernail, or when the sun's out, cover it again, and see if your little fingernail doesn't cover both of them.